So our last two sort of titles or sections of material here have to do with systems of equations. In particular, today we're going to take a look at, and tomorrow to take a look at systems of equations where there are two variables, x and y. And then on Wednesday and Thursday we will expand that to systems with three variables, x, y, and z. So first of all, let me talk about what I mean by a system of equations. A system of equations is two or more equations considered at the same time. We are going to be focusing on two equations, two variables, two equations. But technically, if you had three equations, it would also be a system, right? There are three possibilities when you consider two equations at the same time. One possibility, the first picture, and you don't need to draw these pictures precise. They're just a visual imagery. They cross, okay? So don't get too precise on these pictures. The first picture is simply that the two blue lines cross one another. So they intersect. And that's sort of the point here. How would you describe the next picture? They're parallel, right? That's a possibility. And what's going on the last picture? What do you have, Keely? They're on top of each other. That's a good way to describe it. Sometimes you'll hear it also called the same line. It's just two names for the same thing. Right? You probably have more than one name. My kids call me Mom. You guys call me Dr. Hands. Most of my friends call me Krista, right? All the same person. This is the same line. And it can be written in a variety of different ways, and you've just simply been given two equations that are written differently, but it's the same equation. These are the only three possibilities. There are other ways in two dimensions, two-dimensionally, that this can happen. So there are descriptions for what you're seeing happen here. There are two basic descriptions. And the opposites of them. So let me pause for a second. Let me finish. And a couple of you are still writing. Okay. So an equation can a system can either be consistent or inconsistent. That's one way to describe it. It can also be independent or dependent as a second description. So jot these down and we'll go through them and talk about those last three pictures and which ones are which. Consistent is two lines that have a solution. A solution simply means they intersect at least once. So if consistent means they intersect at least once, inconsistent would mean they don't. And if they don't intersect, it means they're parallel. Another way to describe would be to describe independent versus dependent. Independent are two lines that are actually different. They're not the same line. So dependent would mean that they are the same line. If lines are parallel, they don't cross. Them not crossing means there's no solution. If lines are the same, then they cross at every single point, which means there's infinitely many solutions. So for those of you who have finished writing these four down, look back at those four graphs. We're going to flip back there here in a minute together. Every graph is either consistent or inconsistent. So write which one it is. Is it consistent or is it inconsistent? And then every graph is also either dependent or independent. So consistent means they have at least one solution. So on the first graph, is it consistent? Does it have at least one solution? Yes, this is consistent. And in particular, the one solution it has is where it crosses right here, and my picture shows negative 3, 3. Okay, but it's whatever your intersection spot is. The second graph, is it consistent or inconsistent? Inconsistent, because it's parallel. It never crosses. So the third one's the one that feels weird, but is it consistent or inconsistent? It's consistent. Since it's the same line, I kind of like how Keely said it, on top of each other, it intersects at every point, right? Yeah, so it's consistent. All right, the other words are dependent or independent. Independent means different lines, dependent means the same line. So first picture, is it dependent or independent? It's independent. The second line, is it dependent or independent? Independent. And the third one, is it dependent or independent? That one's dependent. Okay? All right, so when we talk about a solution, we're talking about places where both equations have a point in common, right? We're looking at something usually, picture-wise, that looks something like this. Where do they cross? Or are they the same line? Do they cross everywhere? Or maybe they never cross. So we've got an equation here, example number 1. Two equations actually, system. First equation is 5x plus 4y equals negative 1. And the second one is 3x minus 2y equals negative 5. And the question is, I've got 4 possible solutions. And our question is, do any of them actually work? So we've done this question before, but when we only had one equation. Okay? So in order for it to be a solution, what do you think is going to have to be true? Okay, say that a little bit louder, Sarah. Yeah, it has to work in both equations, right? So we'd actually have to test both equations to see, does this ordered pair, does this x and y make the equation true? So if we test it on the first one, we have 5 times 3 plus 4 times negative 4. Is that going to equal negative 1? Yes, it does. So this is a potential solution because it worked in the first equation. So we try it with the second equation. 3 times 3 minus 2 times negative 4. Does that equal negative 5? It doesn't work, does it? What do I get? I get 9 plus 8. 9 plus 8 is not negative 5. So this one does not work in the second one. So is it a solution? No. So it's not a solution. It's a solution for one equation, but not for the system. Let's try the next one. 5 times 7 plus 4 times negative 8. That was negative. Yes, thank you. Left my negative off. The question is, does that equal negative 1? No, it's a really big negative number actually, right? Because I have a negative 35 and a negative 32. But that's not going to work. Technically, I could stop here right? It's not going to work in either one of them. It happens to work in the other one, so I wanted you to see a case where it worked in, one versus the other, but it has to work in both, of course. So it's negative 21 and positive 16. It actually works in this one. And you don't have to test the second one, but if you did, you actually find again that it's not going to be a solution because it doesn't work in both. So it could work in one equation and not in the other one, and then it's not a solution. Same equations, different points. We've got 5, 0. So if I test the number 5, 0, so you're going to work in my first equation. Five times 5 plus 4 times 0 does equal negative 1. Somebody tell me. No. Thank you, Connor. No, that doesn't work. It actually doesn't work in the other one either. 3 times 5 minus 2 times 0. This also does not equal negative 5. So it could be that the point doesn't solve either equation. That doesn't really make it any more of a problem. It still just means that it's not a solution because we're looking for a solution to the system. Let's try the last one. 5 times negative 1 plus 4 times 1. Does that equal negative 1? Yep, that one works. And the other one, 3 times negative 1 minus 2 times 1. Does that equal negative 5? Yes. So I have to get 2 yeses before this is a solution. So yes, negative 1, 1 is a solution. It's got to work in both. All right, so that's great if somebody gives you points and you just have to test and see which ones work. Where we're going to pick up next time, I'm going to hand out your homework, but where we're going to pick up next time is in how to find them when they're not given to us to just test, okay? We're going to look at 3 different ways for finding solutions. One is with a graph. So, right, if I've got a picture like this, I should be able to just look at it and tell. Or if I don't, I can create a picture to make that work. A second one, and you've heard these 2 before, is substitution. And the third way is elimination. And we'll take a look at both of those next, all 3 of those next time.